Hey AP Chemsters, this is Mrs. Vanderlei bringing you the 14.9 Part 1 edition of Le Chatelier. Le Chatelier is a fun word to say. Say it a couple times. Le Chatelier, Le Chatelier. It's kind of like saying Mufasa, Mufasa. But anyway, Le Chatelier was a French scientist who found ways to shift equations. So if you want to make more products or make more reactants, how can you do this? Actually, this was also used in making the production of ammonia, which really helped change the farming industry, because now they had a way to make better crops, because they use the same idea of Le Chatelier's principles to create more ammonia from nitrogen gas and hydrogen gas. So this is really an important concept that you might see later on. So Le Chatelier is how a system at equilibrium, notice, oh, that's a key word right there. It says at equilibrium. So here, let's do that. At equilibrium responds to a disturbance. What if you change something to that equilibrium? The statement of Le Chatelier says, and to memorize it might not be a bad idea. The reason being, usually this is a written out portion where you have to explain. It's not really a math section, and you really need to get this down. So it says when a chemical system at equilibrium, again, the key word here is at equilibrium, is disturbed, the system shifts in a direction that minimizes the disturbance. So we're talking about shifting right, shifting left. Shifting right means more products. Shifting left means more reactants. So how can I minimize this change by shifting one direction or another? So what is a disturbance? What is a stress? We can change the concentration of either reactant or product. We can change the temperature, or we can change the pressure if you have gases only. You do need to know endo or exo, and please note, only B is the only thing that will change K. Nothing else is going to change the equilibrium constant, only the temperature will. Okay, so let's start with the first one. So it says change in concentration of either reactant. We're going to do all three, so we'll start with the effect of change in concentration. So if a reactant or product is added to a system at equilibrium, the system will shift away, I'll put this, from the added component. Okay, so it'll attempt to use up. If a reactant or product is removed, the system will shift toward that removed component. It will attempt to replace it. So read A and B again to yourself and see if you understand what this means right here and what this means right here. Okay, I'll give you a minute. Okay, so here is an example of dinitrogen tetraoxide in equilibrium with two NO2s, and right now it is at equilibrium. So notice right here we are at equilibrium. How do I know that? Q equals K. That's how I know we're at equilibrium. So the question is, what if I add more NO2 to the system? And what's going to happen? It says now Q is greater than K. So why is that? Go back to Q. Q is product of reactant. So if I add more NO2, so what's going to happen to my numerator? My numerator is going to increase. So my Q is going to go up. And what did that mean if we have too much products in a sense? If Q is bigger than K, the system will shift where? It will shift to our left. Okay, it will shift left to reestablish that equilibrium. So that's how Q can go down. So what if we try this one? What if more N2O4 is added? Okay, so again, I'm going to increase my N2O4. So what happens this time? My denominator, my reactants get bigger, so Q overall is going to go down. So now Q is less than K. How will it shift? Well, it needs to shift to make a bigger number. It needs to shift to make more products, so it will get bigger, and therefore it's going to shift to the right. Okay? Let's see what the next page has to say. All right, so if I were to look at a graph, this is a great picture of what's going on. I really like this. So it says at the original equilibrium, Q equals K. So we're going to start off right here. And what do we do next? We're going to add some NO2. So look what happens, the concentration of NO2 goes up. Now NO2 is right here. NO2 is a product, isn't it? So my products increase. So what happens now? We've disturbed the equilibrium, so Q is no longer equal to K. But what's happened? If I've increased the if I increase the NO2, notice I have an initial increase, but then it goes down. And notice what happens in N2O4, it goes up. So what do I mean by shifting to the left? I'm going to have an initial bump of NO2, and then some of that's going to be used to create more N2O4. So the initial bump, then it's going to come down, and then the N2O4 is going to go up. And what's happened right here, it's reestablished the Q again. So the numbers, that proportion, will end up being the identical thing. So what happens if I'm going to add some more N2O4? So here's my equilibrium again. Oops. Here is my equilibrium again. And I've established it. It's kind of like the same equilibrium as over here. If you look, they're at the same concentrations. But then what? I am adding more N2O4, so I have a big bump. And what happens? So if I have Q is equal to products over reactants, and I increase the reactants, what happens there? My Q is going to go down, so Q now is less than K, so it's going to shift to the right. So if I shift to the right, I'm going to lose some of those, the new N2O4s, but look what happens to NO2. I increase that. So now what? I have a new equilibrium is established, that same proportion as I had before, just different numbers. Do you remember how on previous problems, it didn't make any difference what the initial conditions were? The system will establish a new equilibrium where the K remains constant. The concentrations are going to change, but the K remains constant. And that's what's happening here again. We're disturbing this equilibrium. The concentrations are going to be changing one way or another, and the system will establish a new equilibrium, but those ratios, products over reactants, will remain the same. Okay? So let's kind of summarize what's happening here. So summarizing the effect. Now you have heard me over and over and over again, I don't like to memorize things, okay? I'd like to reason out. I'm not a very good memorizer. So if I just keep this in mind, this Q equals P over R, okay? It doesn't make any difference what they are. Q equals P over R. So if I increase the concentration of one of the reactants, so if this goes up, that's an increase. If I increase my denominator, I get a bigger number at the bottom. What happens to my Q? Q goes down. Well, if Q goes down, that means it's less than K, so it's going to, shift it so that, that number is going to get bigger. I need more numerator, I need more products. It's going to shift to the right. I'm going to have the direction of products so that Q will get a bigger number. What about if I increase the concentration of a product? What if P goes up in the second case? Well, if I have a bigger numerator, then Q goes up. Now Q is bigger than K, I have to make it smaller again. So how to make it smaller? I'm going to decrease the products, increase my reactants. That's shifting to the left. All right, I'm going to make more reactants. What if I shift to the, what if I, decrease one of the reactants? So if I decrease this, I get a smaller number in the denominator. Q is going to go up. All right, so again, Q is going to be bigger than K, it's going to shift to the left. And if I decrease the amount of product, that means my Q is going to go down. So Q is now less than K, and it's going to shift to the right to make up for that lack. Okay, to me, this right here makes sense to me. Okay, I don't memorize this whole thing. I figure it out from using up or down, up or down. And if Q is less than K, I need to make it bigger. I increase my products. If Q is less than K, I need to, I said that wrong. If Q is bigger than K, I need to increase my reactants, decrease my products to make it equal to K. If Q is less than K, I need to increase my products to make it work. So again, I don't memorize, but if you're kind of struggling with this, then go ahead and memorize it, all right? Whatever works for you. But this is like what Le Chatelier is pretty much all about, is the shifting to the right, shifting to the left. How does Q and K, how are they affected? Okay, let's go to the next page. Okay, so problem number 31. Consider the following reaction at equilibrium. Something to look at. Look closely at your subscripts. Solid, liquid, gas here. So you notice what this is. That's a solid. This is a solid. And this is my gas. So if I'm going to write the equilibrium expression, all right, so K is equal to just the concentration of carbon dioxide. So what will be the effect? So if Q is equal to carbon dioxide here, what's going to happen if you add more Q? Well, Q is now going to be bigger than K. And what's going to happen? How do I decrease that? Q value is going to shift to the left, and I'm going to make more, in a sense, reactants, okay? So then what about the next one? Think about this next one. What is the effect of adding additional calcium carbonate? Well, what do you notice about calcium carbonate? Is it part of my equilibrium expression? The answer is, well, no, it's not. So is it going to affect anything? Well, not at all. So there is no effect, no shift. Why not? Because calcium carbonate is not part of the equilibrium expression, the law of mass action. So nothing's going to happen. It's going to sit there. So it's kind of like this. I liken this situation to, all right, what if I really like my sweet tea? I put in a whole bunch of sugar in it. All right, some of it's going to dissolve, but what if I keep adding more? Doesn't eventually, it's just going to sit there and do nothing? And that's what's going to happen here. If I just keep adding more calcium carbonate, nothing is going to happen. I'm not going to make any more carbon dioxide because it's not part of the equilibrium expression. Okay, this next one I think is kind of fun. I will try to have this set up as a demo for you when you come in again, and it's really neat to see. It's a good visual for what's going on with Le Chatelier. So if you have more reactants, it's going to be blue. If it's going to be more products, it's going to be pink. So you can literally see what's going on. All right, so what if more water is added? So if water goes up, well, where is the water? Water is on the reactant side. So now what? Q is equal to P over R. What happens? R goes up. Now think about what happens if R increases. What's going to happen to Q? Is Q going to go up or is Q going to go down? If you increase the denominator, Q gets smaller. So Q is going to be less than K. What's going to happen is going to shift to the right and it's going to turn pink. Okay, well, what about the next one? What if we have hydrochloric acid? Well, where's hydrochloric acid in there? It's not there. Oh, look right here. Chloride is there, though. So if I increase H2, or I'm sorry, I'm saying that wrong, HCl, well, for heaven's sakes, my chlorine is going to increase. So if my chlorine is going to increase, all right, so Q equals P over R. If my chlorine increases, what happens to Q? Q gets bigger than K. How is it going to shift? It has to minimize that effect. It's going to shift to the left, and therefore it's going to turn blue. That's why I use blue. Okay. Now look at letter C. I like letter C. And we can do this too. What if silver nitrate is added? And you're like, well, holy cow, silver nitrate is not even part of the equilibrium expression. Where is it there? Well, what do you know about silver nitrate? Well, silver ions, what one of those things is going to affect the silver ions? Well, I think it's going to be the chlorine. So what happens? I'm going to make AgCl. And what happens to the amount of chloride then? Okay, the chloride is going to go down. So if chloride is going to go down, Q equals P over R. If chloride is going to go down, what happens to Q? Q goes down. It's going to be less than K. It's going to go to the right, and it's going to turn pink again. That's why I shifted colors. Okay, and what about the last one? If water is evaporated, so if I use water, I probably should shift it again, huh? What's going to happen? Well, Q is equal to products over reactants. So if water goes down, reactants goes down, Q gets bigger. It's going to shift how? It's going to shift to the right. Oh, sorry. Yes, it is. No, it isn't. It's going to ship to